but the
Who did that?
you did.
What does all the wiggles in the mirror do to your image?
Makes it bad.
Okay.
Here, let me go and show.
You're saying you average it out and it's okay.
Yeah.
What does that do to the image? Is that still average it out or is it not okay?
I'm not sure if it's due to the sampling process of the software and the camera, or just the fact that the air is unsteady. The idea is you want to average them a lot. You can see the variation between one image and another just by taking multiple images, and it has to do with the air density and all that, and turbulence, and also thermal gradients. With the air being colder at the bottom than at the top of the mirror, and that actually can be seen. So let's see here. Let me just, as I talk to you, oops, something is, oh no, something's in the weeds here with my my program. Oops. Okay, hold a second. Inverted.
Just showing the bath interferometer kit there to Bruce. Bruce, have you seen this one before?
No, I haven't.
Yeah. Let me.
You probably understand that part of it. So Mike got this kit and he's been messing around with it and getting images. That looks like a thumbprint, but I guess that's typical.
Yeah, let me, I can share something with you.
Okay, I'll stop sharing.
Okay. And let's hopefully I take the right ones. Hold a second. Here we go. Okay, so this is an igram, okay, of my 14.5-inch mirror. Okay. And so I'm getting pretty good. I got a polarizing filter that's helping to get better fringes. As you can see, this has got like a gazillion fringes, which is good. And so the first thing you do is you have to tell it where to look. And so what I've just done is I've drawn this circle around here showing where I think the mirror is, okay? And so you hit done, and now you get a Fourier transform of the data. And so this is the DC component, and this is the AC component, and the idea is you put a filter just before these round discs here, and then it computes it. Okay, so this is what we're left with. And so let me just go and.
Did you say there was an AC
high
and
spots on the edges, 2 places?
Yeah.
Is that what that's saying?
Yeah, it is. And that could be due to the whoops. And I can go do a, hopefully, let's see here. I'm going to go full screen. Can you see the full screen part?
No.
No, it's
okay.
Little image in the middle.
Okay. Okay, let me just do a stop share. Start share. Okay, so here we go. Okay.
That's better, yeah.
Okay, okay. So these controls over here, I'll adjust sort of like the sensitivity and the 0 point or whatever you're looking at. Okay. So what this is, okay, if we go over here and it's saying, whoa, I'm up to 4 wavelengths. This mirror is a crappy mirror. Okay. It's technically a crappy mirror.
This one's already been illuminized and everything?
Unfortunately, so it's gonna be coming off of it. But as you can see, the center is low and this is high. And this is mathematically saying if it was completely flat, that would be a perfect mirror. Okay, a perfect parabolic mirror. And I can set up the software to take a look at a spherical mirror too, to determine how good a spherical mirror is. Okay.
Mike, well, you said if what is perfectly flat, it would be a good mirror. What are you talking about? What part of that?
The surface of this here would be completely flat if it was a perfect parabola.
Okay, yeah.
Okay, so I'm going to do a stop share.
And this mirror you had there, which mirror was that of yours?
This is the 14.5-inch mirror. Okay, so let's do a screen here. Okay, so it's saying that my wavefront is RMS of 1. It's a bad mirror. Okay, it doesn't even have a Stroll ratio. So if I go over here to this point right here, the profile, and let's see here, not nanometers, surface area. Okay, so what this does, if I move this over here, this is another formal way of viewing it. Okay, and what we're doing, as I turn this around, you can see that line there goes across it. So it's taking a segment of the mirror from edge to edge. Okay, you can see how it's been moving around. Okay, now some of this is due to, if we go over here to the Zernike terms, which is a way of saying that you have a bunch of functions that describe different aspects of the mirror. Like in this case here, defocus. I'm a little out of defocus. I probably should have gotten a different one where you want this to be close to 0. This is my
That would be a flat line if everything was hunky-dory.
Yes.
The profile?
Yeah, the profile. Okay, these are astigmatism. This is what they call trifoil. Coma looks like a potato chip. Trifoil looks like a ripple potato chip. And second order astigmatism and coma and all that. And there's basically, I think, 70 terms in total that are used to describe a mirror. It doesn't describe it perfectly, exactly, but it's close enough. In other words, you start adding up these things, these terms here, and you get a better and better approximation of what the actual mirror looks like. So going back to this point here, okay, down here it says that I've got a Gaussian blur of 9% of the diameter. If I go down further, all of a sudden you can see where you get, notice how it's kind of ripply effect. Okay, that's just the noise in the data. And in this case here, oops, okay, that edge wasn't properly defined, and so it found this as an error. This could be causing some of my RMS data. So if you take a look at the RMS data while I apply filtering, okay, it goes down. You notice how it's now smooth. So part of it, I think, is just the noisy data. I'm trying to ask more information on there. Okay, so now part of it would tell me what does the star test would look like. And so it says it looks pretty awful. Although, and this is what get me, and I have to, and the George, who sold me the interferometer, who's been in contact with me, says, need to go back and star test again. I did not see star testing this bad. Okay, so something must have happened to it. And this here kind of shows the Rankine-Foucault measures. As you can see here, it doesn't look too bad, but obviously it's a bad mirror. Now, that's my mirror configuration. Let me make sure. Okay, that's for my 14-inch. Okay. Okay, so let's go and find another image with my 10-inch. Okay.
That's the one that you were building at the museum and
Yeah.
that you've
Okay.
got some really good pictures through.
Yeah. Okay. So I think this is it, although I'm not sure. Shoot. Okay. Bear with me here. Sorry about this.
Of what is that a picture?
This is your interferometer.
Oh, okay. All those red pictures were just the interferometer.
Yeah, because it's a red laser.
Okay.
Okay, so let me try something here. Okay, so that's the 14-inch. I'm having a little difficulty here. Please stand by.
Can you use a green laser with this system?
No, you could use a green laser, but a red one. And it's very important to know the light frequency of the
Laser.
of the laser, because that matters in how things are done. Okay, so I think this is my 10-inch. Yeah, I know it is because the circle is smaller. So I'll go to my mirror configuration. Whoops. Configuration mirror. Okay, doesn't, oh, wants me to do this first. Okay. So I go zoom here on the edge. And
I thought red lasers were more like 620 nanometers. You showed 550 nanometers.
that happens to be the wavelength that is measured on that particular laser.
Really? I thought, well, green is 545, isn't it? Nanometers.
Okay, hold a
Don't
second
know.
here. Okay, hold a second here.
Right now he's showing igram laser wavelength at 657
Yeah, right. I'm
nanometers.
trying to, okay, this is blue. Okay, let's do this again. Okay, so it's oriented differently, so the frequency information's different. Okay. Oh, this is another, okay. I'm gonna have to find the time when I actually did do it. Oh,
Now, this is all data and measurements that you've done since you finished the mirror, and this is all new
Yes.
stuff that you've learned?
Yes.
Okay.
That's right. So for better or for worse, it's whatever it is.
Well, congratulations.
Okay, so let's see if I can
Yes.
find something. Let's see here, open. Let's see, go to the USB. Oh, okay, USB drive 14. Okay. Oh, second here. I need to, don't want to. Okay. Sorry about this. Okay, so I think this is my 10-inch.
Amazing software.
It is, and it's free. It's all done by a bunch of guys that are into this.
So you
Okay.
take a picture with your camera as a TIFF, and then you import that picture into the software.
Yeah.
And it does all this stuff.
Okay,
Is that
so I'm not finding, let me try and find the report. Okay, hold a second here. I'm gonna do a stop share and try and find the data here. Sorry about that, guys.
No worries.
But anyways, depending on the
Wikipedia says green laser is 520 nanometers. Blue is 445 nanometers. Blue violet. Red 635.
Okay. The eye is most sensitive at 545. That's the blue green. I mean, yeah, the blue yellow green. I'm sorry.
Okay, so I think I got something here to show. I just need to. Okay, I'm going to do a share here and we'll go look at the report. Okay. So what happens is that you get this report that prints out. Okay, so it says here, when I did a lot of smoothing, okay, here's my 10-inch. Okay, F5 5.9, I got a strail of close to 0.86, which is pretty good. Okay. And so when you put this number together, the 254 millimeters with the 297, you have a null here, a number that tells you what the difference is between a sphere and a parabola is. So we go down here, you can see on defocus, I had very little defocus. I had less than a wavelength. And the way that I got that was I didn't do it how they normally show me on the video. I used backyard EOS to take a picture, got a test picture, put it into DFTFringe, went through the whole thing until I saw the Zernike numbers, and then I dialed in the focus until I got the least amount of defocus. So you can see here my comas. You really don't look at the coma because that's going to happen with parabolas. But my astigmatism's pretty small on this one here. My spherical error is less than 1/10 of a wavelength.
That's great.
And we're talking about trifoils and all that weirdness actually is pretty low. You take a look down here, most of the terms are very low, except for my 14.5-inch mirror, which is all over the place. Okay, so you first get this here, and they go up to 47 terms. Now, the one thing you have to notice, there's several sphericals. Okay, you have this term right here, spherical, and you go down, there's a second spherical and a third spherical. And so basically what it means is how lumpy is your spherical correction or how smooth it is. If you have a higher, like a second order spherical mirror, it means is that when you did the parabola, you kind of pushed it down and moved things out. And it's sort of like it wasn't a nice parabola. There's a zone, okay? So we go down here, this is what it looked like. And so you got to remember, that these contour plots are very, very small, the error, okay? We're talking about wavefront errors of, 1/10
of a nanometer, right?
Yeah. Okay.
But Mike, why is it 550 nanometers if the red laser is 620?
Because when the guy measured that laser, it happened to be that value. When the guy ships you a laser from this company, he measures all his lasers and sends you a piece of paper with the
Well, you would think that the laser would look more green then.
well, no, it's still red. Okay, in this case here, it was, okay, this laser that he sent me.
Looks like the colors relate to the error over there.
Yeah, right,
the
geometry, yeah.
Right, they're not the color of the wavelength or the laser.
Okay, so this one is the laser he just sent me is 658 nanometers. That's what it is.
Right,
okay.
But the wavefront error is being shown at 550, so it's being normalized to 550.
Oh yeah. Oh, I'm sorry. Yes. Okay. Basically, what is you do the measurements at the red laser wavelength, and then the software smart enough to say, well, what does it really look like at the most sensitive wavelength to the eye?
Thank
you. Okay, because at red, things are more forgiving than at a higher optical frequency. Okay, so this is the contour plot. Okay, and this is what it looks like. You can see compared to the 14-inch, there's not much of a hole here. But I guess every mirror maker has their own signature. In other words, their own habits or peculiarities that that tell you that this guy's more likely to do this with his mirror. Okay, mine is producing this value right around here.
It looks delicious.
Yeah.
Well, so yours is like good in the middle and high on the edge, all the way around.
Right. Yeah, right. The way I do it. Okay, so here we go right here. The profile.
Oh, yeah, that shows it.
Profiles. Okay, now it goes, you go, oh, well, this is terrible, except for one thing. The top red line and the bottom red line are 1/8 of a wavelength.
Right, so you made it.
Yeah, that's
what were you looking for?
We're looking for
actually less than 1/8 of a wavelength. They're more like 1/16.
We're looking for a straight line for a perfect Still ratio. Okay.
Right, but
okay, so if we go back up here, okay, the Still ratio is 0.859.
What does that mean?
That means it means that 85%, 86% of the light that should go in the center of your airy disk goes in there. It's actually a very nice mirror. Okay, so again, and so here's the hooks for the star test, point spread function and modulation transfer function. The star test is that this is what it would look like in the star test. And yeah, I was seeing that pretty much. And I knew that it wasn't quite, I knew there was a slight difference, but I couldn't categorize it. And to tell you the truth, I need to learn how to do star testing a little bit better than I did before. So this here, your point spread function is basically the thing where where they show the central point, it goes down, you get your first ring and your second ring. That's what this is all about. So if this red line, whoops, okay, if this red line was up to here, that'd be a perfect Still ratio, and this is the theoretical, whoops, something, my computer's doing something weird here. No, I don't want to. But anyways, so it says that instead of going to the black, it's to the red. So you can see that the central spot is less intense by, we're talking about a few percent, right? And it's all moved into the higher order stuff. Okay.
Really cool.
The modulation transfer function is kind of shows you what you're likely to see with planetary objects. Okay. This is low frequencies, large things, and this is high frequencies. And as you can see right here, at the various highest frequencies, I have very good performance, and then it starts going down like this here. Now, if you were to take a look at the book on star testing, it would tell you it doesn't take much to take this and bend it down this way. Obviously, we're talking about, and this is sort of simulated Ronchi. I could move the slider up and down, and that's like moving the Ronchi in and out, but it only does it for one reading here. And here is the, come on, where are you? The interferometer, interferogram that was using. Not perfect. And this here, error in waves, this was talking about the error that the software was having some difficulties with in certain things. So this is my 10-inch mirror, okay? as opposed to my oops. Okay. Let me try and get a, oh shoot. I got too many windows up here. Sorry, folks.
You have to clean your windows.
Yeah. Okay. Let's go and.
Sorry, I was late. I had computer problems here.
Uh-oh.
Okay. Hold a second here. So
Were you
You have to
waiting
get
long to
Neil
let me
deGrasse
in?
Tyson to make them good.
No, I wasn't waiting long.
Okay.
Okay. Hold a second here. Go to USB drive and why is my. Let's see if this one, no, that's still the 10-inch. Okay. But oops, let me go and do this again and show you the effect on the surface, the noise of the data, what it does. Okay, so I think that this is it should be a 10-inch.
Jerry, Mike's been showing us his interferometer diagrams and the software and how he's got the 14.5 was not the greatest, but his 10 is under 1/8 wavelength.
Oh, terrible.
The 14.5, but the 10-inch is good. Yeah, real good.
Yeah. Okay, let me just get this again here. Okay.
But the diagrams show really, it looks terrible on the diagrams, but then you have to realize that it amplifies everything.
I don't know
The
why.
height is stretched.
Okay,
Yeah.
hold a second.
That's
Let me,
called AGC. That's automatic gain control. It always expands it so it makes it a certain size. Then you got to look over it on the x-axis or y-axis and see what the actual numbers are.
Yeah.
okay, I'll just use this one here. I don't know if I have anything on the screen yet or not.
No.
I'm not. Okay, let me just go do it again. Share screen. Okay, on this particular one. Okay, hold a second. Why is you got oh this Zoom stuff gets in the way, so whoops. Sorry about that. Okay, you can see here how when I have little Gaussian blur, it makes things look really bad, okay? And then when I increase it, all of a sudden it looks better.
Smooths it out.
Yeah, so I tried to ask George, and I don't think he understood my question, is how much of the Gaussian blur do you really need to, is a valid thing? Because it could be that when you have no filtering, you're up against mathematical, just, little mathematical things that are causing this type of thing. It could be sampling problems or something like that.
Well, I was going to ask, what precision is it? I mean, your camera has probably got 12 or 14 bits of resolution, but if the
No,
image
it
you're
isn't.
looking at
No, it
is
isn't.
way down on the bottom.
No, the problem is that I'm using JPEGs. And so that's only
Oh,
8
yeah,
bits.
they throw away the low-level information.
And I think that if I were to go, I'm pretty sure that I'd have to. That might do TIFF. I don't know, but everybody seems to be using JPEG, and
Not high.
well, I know you're special.
Well, I've actually done astrophotography using both JPEGs and TIFF, and I looked at the results, and I really can't see much difference, if any.
That's because your eye uses JPEG.
Oh, okay.
I'm just joking.
Let's see here. Well, I had another report where I was doing the the 14-inch, but the 14-inch is so bad it doesn't even get a stroll ratio.
Huh.
But
Well,
But it gave such good star tests. How could that be?
I don't know. So George said for me to go and do some star testing to verify that. And it could be that with the windy conditions and also
Yeah,
with the fact that I might have been not focusing exactly the same on either side of the focus. Because, you know, I didn't have a micrometer on there. I was sort of like rotating like a creaky focuser, you know, you're not likely to have the same amount. You know what I mean?
no, the when you go either side of focus, the blur should be the same size. So you don't
Yeah,
need the
but that
micrometer on
assumes
the-
that you're moving it the same amount. When the mirror on the 14-inch, when it showed me the results, the circle of the star test at the out of focus is
Yeah.
different.
Hmm.
Yeah, so
Hmm.
yeah, I
You should be
know.
able to- Mike, you should be able to get the same image and
Oh.
be able to, I mean, to assume that you're at the same distance on either
Yeah.
side. In other words, your rings are going to be somewhat similar on both sides of focus.
Yeah, well, maybe I was just deluding myself of, okay, so here, hold a second. This Zoom stuff
So
gets in
Mike,
the
did you
way.
get an answer from George about how much Gaussian blur you should use?
No, not yet. I'm gonna find out. I'll ask him again. Okay, so here's let's go back to this here. I need to, let's do auto. Okay, so I don't have it properly on this one here. So let's see here. So the idea is to get the outline perfectly on the, whoops,
perfectly centered.
center. It's got to be perfectly centered or else things blow up. Okay. And so George was going, well, what's these big things here, divots? And I had to write back, that's where they supported the mirror when it was being illuminized. So one of the things that we can do is we can take the region and kind of like draw against this one and draw it against that
So this is
one.
like path integration.
Yeah. And this one, there's the other. And you know, some of that might,
Could be another one at 2 o'clock, but it's not.
yeah, well, yeah, it's because of the fact that things aren't all that great. Okay,
What's at 7?
what, this here?
Yeah.
That's the null. Basically what they want you to do, this would be in the center. Okay, that's when you go focus. Okay, there's your null. But what they want you to do is like tilt the mirror. That's how it finds the surface. It doesn't look straight and dead on. It looks at the surface. It's like us picking up our mirror when we're starting and looking, oh yeah, it's concave, you know.
Oh, okay.
You know, there's out of focus. Go back to that one that you just had. There's out of focus diffraction rings, very big ones all across your mirror. I'll bet you're having problems with the lens that you put in the bath interferometer.
Well, this might have been done before I had my my polarizing filter on.
Okay.
Okay, so it says it's a parabola. Okay, compute. Oh, out of memory. Oh, okay. It just crashed on me. Sorry about that. Let me bring it back up again. It's good software, but occasionally it has its moments. Okay, hold a second here. Let me go back to here, share.
Jerry, have you worked any more on your interferometer?
No, I've got too many things going on here.
Yeah.
So we've got a sick dog that's recovering from surgery, and
COVID. Oh,
No, nothing like that. It's just some golden retrievers. When they get to be 10 years old, they start accumulating benign tumors of fat deposits.
Oh, yeah.
And one of them was on her armpit and interfering with her range of motion. So we had that removed.
boy, she's pretty young too, like maybe 3 years old, maybe.
10 years old. She'll be 10 in September.
Oh, I can't believe she's that old. Wow.
I know, it goes quickly. That's the problem with pets, is their life just streaks by so fast.
The bigger the dog, the shorter their life.
Okay.
Yeah, that's right. This is a 100-pound dog.
Okay, so folks, here is how it looks now. Let me go and get a full screen, and you can't see this. What I'm going to do is get this surface to look better. Not better, but okay, so I have some. Okay, so I have some crap on the side. That's because I didn't get it proper. It was there were problems with the camera setup. Okay, but you can see here it's like a donut some old person would sit on. Okay. And the profile waveform area, you can see, is way more than 1/8 of a wavelength. So, and I go to my star test.
Now, this is your 14-inch?
Yeah, you know, this is not a great, I need to go find something that's a little bit better. Okay, compute. Oh, one thing I forgot to do, folks, and in his videos, he talks about it. Come on, move this over.
Where are the videos located, Mike?
It's from his website. They're there. Let's see here, tools, configuration, mirror. I need to make this 14.5 inch. 14.5, 3.95. Okay. Okay, so there we go. And of course, it's not, I have, you can, you make a slight mistake on it, it'll cause you grief. Yeah, it doesn't see that the diameter here on the thing here is not proper now.
That's because you've got the radius here in millimeters and you just put it in inches.
Okay, let me maybe that's the reason. Okay, millimeters. Okay.
Well, no, you see the
yeah,
radius.
that's it. That's it.
Okay.
Okay, cool. Okay, so okay, so this is, I have problems with the photograph, but you can see here it's kind of a lumpy mirror.
Yeah.
And
which doesn't make any sense at all.
yeah, well, it could be because it's a thin mirror and it's on posts instead of a sling. And also because it's a crappy mirror. Okay. So you can see
I still think you're on a learning curve. I don't think we can jump to the conclusion that it's a crappy mirror.
Well, because my 10-inch looks so good.
Yeah, but your 10-inch is a thicker mirror.
Yeah.
And it doesn't have the flexure that this one might have. You need to suspend this one properly.
Yeah, okay. And I got some hose clamps.
Where is the quarter wave on this on your lower image here?
It's twice the 1/8 inch or the 1/8 wave.
Yeah, right. So they're really close to each other. It's saying that
those are 1/8, yeah. So it looks like this is about a half a wavelength.
Yeah.
Plus or minus.
Yeah. So going to a star test again. No, I got much better than that. So this is a bad picture. I'm gonna, I could jump out here. Let me just do one thing. Let's do, and I can't move this top
But
part
you
here.
know, Mike,
Let's-
also it's a 14.5, but it's a 3.9 F ratio.
F3.9.
Yeah, let me show you what the correction is for a perfect mirror of this size. Okay,
I
correction.
mean, that's going to be hard for a thin mirror to get good returns. With the flexure, it does at 3.9.
It's all in the mounting of the mirror.
Okay, so this is an interferometer simulated of a perfect mirror. Okay,
But your lines are much closer together than this.
yeah, I've got more. Yes. Okay, let's see what we can do here, folks. Oh, it looks like it doesn't like it. I'm gonna, oh, there it is. Okay, so this is a perfect mirror.
Looks like a blank.
Yeah, well, yeah, there's a little bit of, this is probably due to the mathematical. If I were to go get my 3D things there and try and look at sensitivity. Okay. Yeah, there we go. So you try and, you know, you're talking the wavelength is very small, you know,
Looks like
practically
you got a turn down edge on your perfect mirror.
I think that has to do with the mathematics. Notice
Yeah,
in one case here, it goes up and a little bit and down. I think that's just a simulation round off error.
okay.
We're talking about, you know, okay, RMS waveform 0.016. Okay, you know, that's down in the mud. Okay, so you go to the point spread function. Okay, so that's what it looks like.
Mhm.
So they're pretty much the same, although the way the mathematics gives it, they're slightly different in size. So I'm not sure why.
Mhm.
And you go to the point spread down over here, point spread, it's right on there. So I think this might be mathematical round off errors or whatever. The modulation transfer function of,
Mhm.
you know, that matters with planetary detail says that this is a perfect mirror.
Mhm.
And now we go for our Ronchi. Okay. And so let's move it up, you know,
Yeah, there's the Martian face.
yeah. Okay. Going and way outside.
Mhm. Nice donut.
Yeah. Okay.
Uh-huh.
And of course, on the Ronchi, we tend to go for more look at this at even further away from the focus point. But it's interesting to note that this here is saying this is at a perfect focus. And it's you know, it seemed to me that it seemed to me that was like inside focus, not at perfect focus. But
I would say so too.
so I'm not sure if there's something in here that's saying, no, it's, we go over here. Now we take a look at our Zernike terms, okay, which are a bunch of functions, okay. They're orthogonal functions for you guys, which means that each one of these is a different looking type of function and they all add up.
Mhm.
They don't affect the other ones at all mathematically. So you're talking about, and you notice there's a little bit of number here. I would expect that if it was a perfect mirror, all these would be 0, but they're not, except for X and Y tilt. And
Now,
as
there's no data going into this. This is all just mathematical functions that has input.
that's
But
right.
no data input.
This is your simulation. Yeah.
Yeah.
So we're talking about round off error, you know, you know, least significant digit, you know, type of thing, maybe, you know, a plus or minus 1 on the smallest digit.
No, but at the
So-
radius of curvature, you should not have these ronchigram looking like that.
Wouldn't that, isn't that a perfect parallelogram? I mean, a perfect parabolic mirror to have those
Yeah,
kind of
inside
curved lines?
focus, but not at focus.
Yeah, so I'm not
Well,
sure.
don't you have curved lines at focus?
No,
Should be nulled out.
yeah. Should be
Yeah.
uniform gray.
So this, let's see here, go down to here. So I'm not sure what, okay, I think,
You're simulating a mirror that's slightly off, not a perfect mirror, I think, somehow, but it's got a real good Strel ratio.
yeah, that's what matters, right?
Well, it's one of the parameters that matters.
Well, other than the fact that low scatter, right?
What is the Strel ratio? Is it,
It's the percentage.
Picture a circle and 98.989 of the rays that you're tracing to get that, they travel through that circle.
Right.
Okay.
This here, the point spread function down here, which says PSF. So this basically says it's putting all the light in the central spot. Okay. Of which,
Okay.
but it's never 100%. It's always what, 83% or something like that for perfect.
Yeah,
or something.
you know, what I was going to say is that, you know, in everything that I've read, there's just too many people that say there just is no perfect mirror. It just doesn't exist. It's gonna, those numbers you were talking about.
Yeah,
you
but
know,
mathematically it does exist.
well,
so it may not
then they
exist
should have
real.
all been zeros. And I think that the
Yeah.
software, I don't think the
Oh.
software could go there.
The
Tim,
PSF
you just-
function is a cross section of the interference, the diffraction limited diffraction pattern. Go ahead.
Tim, you have to go to the meta universe.
That's it. We should be working in phase space here.
Yeah.
You know,
So-
I seem to remember doing star tests, and Mike was saying the Y is one larger than the other. And I seem to remember seeing that at the eyepiece. And I don't understand it either.
Yeah, look at this one here that shows the one on the right is different than the one on
Yeah,
the left.
I can see that. But if you think about the rays, the cone of rays converging to the focus, the same distance on each side of the focus, unless the rays bend, they should be the same size pattern.
Yeah, so I'm looking. Hold a second here. I'm measuring off my monitor.
Maybe this is just illustrating how little I understand this.
Okay, 1.1 and 1 3/4, and the other one is 2 and about 1/8. But it could be, it could be just, it just could be the fact that what they want you to look at is how the rings look like rather than the size. It could be there's some slight, you know.
You see, I think that's right. I think you're right on that. Because I think you want to see a similar amount of rings and a similar pattern.
Yeah,
And you
and a
really,
similar size.
and
If you're
you're,
equidistant on each side.
uh-huh. And I think there's some that they then in Souter's book, I think that you really want to pay particular attention to that outer ring, because inside and outside focus, it can one can be brighter than the other, and you still have a really good mirror. But I don't understand it. Souter's book.
Okay, so let's go to
good
this.
stuff.
Let's go to the spherical aberration and try and change it. Oh, it's not going to let me. But
What about if you go up to the word defocus? See the field up there toward the top?
okay, yeah, that's like focusing in and out. If I
Yeah.
go down. Okay, so it's
So everything the out of focus images got dimmer and the focus got brighter. So go to 0 on that. Run it
Okay,
down to
so-
defocus down to 0.
okay. I suppose I could just type in 0, but
I think you can, but you're there anyway.
okay.
So this is what it looks like at focus.
Yeah.
And they're both, yeah, and
So it's the mathematics or the
but
the
wait
way
a
they're
minute,
scaling things are slightly different. It looks like.
then what do the two wing pictures mean? I understand focused is the diffraction pattern at
The
focus.
center one is when you're at perfect focus. The
Right.
other one is when in and out of the focus.
But it's not 0 waves out. You're at focus already, I guess that's
Yeah,
just
right. It's
yeah.
just that the center
So why
one
aren't
is
all
much
three
bigger.
of the presentations the same?
Yeah.
Yeah, well, these are probably the ones on the wings are a larger scale. Okay, and this is the one focus is probably closer in. Okay, that's probably what the deal is. If I go to like one wavelength. Okay. So I think it's a matter of scale. The two side ones are there because it just needs to be that much bigger.
Okay.
Well, now you're getting into the area disk that should go
Yeah.
3
So-
waves and 4 waves and whatnot.
Well, the area disk is the central on the focused image.
Yeah. So
Aren't we looking at area disks there on the left and right?
Those are
No.
expanded. Those are just out of focus diffraction patterns.
right. Yeah.
Oh, okay.
Man, I just don't understand that. I don't understand why one gets larger.
I don't either.
Because it's not exactly in focus. Well, but it says minus 7.7 plus
Yeah. Right.
7.7.
I'm
Yeah,
going to have
They're
to
equal
ask.
sides of focus.
Okay. Send me an email in case I forget. I'll
Okay,
ask
back to
George
the old books.
why they look different.
Is there a possibility that it's because you're inside focus on one and outside on the other, that because you have different distances there, and they're not significantly large distances, but that's
No, but
why you
Tim,
get that
Tim,
magnification.
the differences are supposed to be equal.
Yeah.
One's 7.7 waves and the other is 7.7 plus 7.7 waves. It's
Yeah, but
supposed to be-
Jerry, I think
Okay. I got my book
may have
out.
7.7 waves, and maybe the magnification is different inside than outside, so you may have a larger image.
Yeah.
That would mean
outside
that there's
the
a
inside.
nonlinearity in there.
Or it could be just the way they scaled it, and it's a slight bug, but it's not considered to be a deal breaker. What on our igram? Okay, why don't we go for something that's not quite spherical? Let's go for 80% or 60%.
What if we do 0% spherical?
Oh, 0%. Okay, I can do that.
What will that mean?
Okay. This is a spherical mirror with the interferometer gram. You notice that it's straight all the way across. Okay.
Yeah.
Okay. So we'll do an analyze and we'll do the results.
Uh-huh.
Okay. And okay, something happened here. Okay, let's do a wavefront. Okay, spherical 0. I'd probably did. Okay. This is okay. So this is what.
Uh-huh. Yeah, now that's believable. It's a sphere, and so the conic constant is 0.
Okay. Yeah, you notice how on the profile
Yeah,
it shows up and down. Okay.
yeah.
Okay, so we go down here to our Strel ratios. Okay, we kept the same tilt. We didn't do any defocus or anything like that.
Right.
Astigmatism 0,
Mhm.
but our spherical is now 2.961, which for a mirror this size, I guess, is a 0 correction in
Mhm.
spherical.
Yeah, you've
Okay.
got spherical aberration in it.
All right. Okay, so now we go to our star test. Okay,
Mhm.
and notice that it's okay. First point spread function, it's way down there.
Yeah,
Okay, our modulation transfer function, which means
it's just
how
terrible.
well terrible for planetary stuff.
Yeah.
Okay,
Okay, that looks good.
that looks as it should, not good.
Right. I mean, it looks believable.
Yeah. Okay, Ronki. Okay, Ronki. Okay, there we go. Okay, so we're gonna go in. Okay, that looks like a sphere
Yeah.
without a turned edge.
Yeah.
Okay, and so
I've
Go to
never
we-
seen that.
Go to 0.
So
What?
that's what it
Go to
looks like.
0.
okay,
Okay,
There's your ring.
that's working.
okay, it's working.
So now let's go to a perfect parabola.
Okay, I did. That was the previous one.
Okay, let's do it again.
Okay, okay, hold a second here. It's not doing the
Well, the
thing.
conic constant is 1. That's what you need for a perfect parabola.
Right.
That defines the parabola.
Okay, so we
really?
go
Yeah, so-
correction. Okay, so correction again is,
Well,
Okay.
wait, why do you need any corrections? No, the perfect
no,
parabola.
no, for a perfect parabola, correction needs to be 100%. Okay, here we go. Flat surface. This looks flat because that's compared to a parabola. Okay.
Right.
Okay, so now profile. Look.
Yeah,
it's
that would be a very nice mirror.
very nice mirror. Well, Stroll 1.0.
Yeah,
Nobody
perfect.
would. Okay, so star test. Okay, there you go.
Oh,
Yeah,
there we go.
see, they're equal size on each side.
Yeah.
For some reason, the last time it didn't give the proper.
Yeah.
I don't know. Okay, so and now we go to our Ronki.
To my eye, the one on the right is slightly smaller than the one on the left.
Hmm,
Okay, so this is at 0 point.
yeah, I don't believe it. At focus, assuming the 0 is at focus, and that should be a gray disk.
For
a
Ronki,
parabola.
for Ronki?
For Ronki, yeah.
No,
should
this
be
is a
gray- it
fast
should be
mirror though.
Yeah, that's okay.
Should be null.
Yeah, it should be no.
Okay, so why? Okay.
So is a perfect spherical mirror, is that the same as a perfect parabola?
No,
No.
very different.
Yeah.
A perfect sphere is loaded. It doesn't focus to a point in a plane. It focuses to a conical-like surface called a caustic. And
Yes.
that's why, for example, the Arecibo radio telescope, which was a spherical telescope, had this large antenna that hung down because that's where it had to pick up the radio signal from a point source because it was spread out along the line because of spherical aberration.
Okay, so we took a look at the point spread function for this one here, and somehow the previous one wasn't, something was amiss in the clicking, because right now you can see they're just
Yeah.
barely,
It's a better fit. But
Yeah,
Bruce
better
is right. The one on the right looks slightly smaller.
yeah, it does.
So whatever we did wrong before, we've done the inverse of it this time.
Well, yeah, take a look here and introduce some astigmatism and other things in here for,
Well, that
Well-
astigmatism wouldn't make the circle bigger, I think.
but it
Boy,
calculated,
that's getting way down there. Third order coma.
yeah. So anyways, let's go for simulation of let's say what, 80%? Okay, and done. Compute. Okay, so here's 80%.
Right, an undercorrected mirror.
No, now that's going to mean that the center is
Too
Higher.
high, and the edge is too high.
Okay.
Okay, and so here we go. You can see
Mhm.
here the difference.
Oh, wow.
Wavelengths, okay? Okay, now let's go for a slightly better mirror. This is fun. 90%.
Show me
It's more
Tim's mirror.
It's more I forget where the turned edge is. Sorry,
Tim, you're
Tim.
gonna have to send your mirror to Mike.
Yeah,
Okay, so now this is closer.
Yeah, it's getting closer.
Okay. And
So if you go to like 95 or 96%, you'll probably be within an eighth of a wave.
so notice how in the MTF it's better at the higher spatial frequencies.
Yeah.
Notice how the red line is climbing up to the top here, and you can see that you know, the first ring is a little bit more. You can see that in the focused area here. Okay, so now
Hey, Mike,
simulation.
what does spatial frequency mean? I don't get that. What is that?
That is the size of the detail like on a planet.
Yeah. High spatial frequencies, see out at 1 on the horizontal axis, you're out at 1. That's the highest spatial frequency that you're capable of resolving. It's the finest detail that will show non-zero contrast.
So in other words, lower the spatial frequency, the larger the features, but in the case of a mirror, that means that you're not resolving fine detail, but only large detail. But in this case here, it does a fairly good job, and then it falls down on itself. This is where a lot of mirrors where things look soft with the planets, like belts and stuff like that, where the spatial frequency or the size is not as good as the higher stuff.
Let me explain with Tom a little thing. If you look at let's say you have a screen that you're looking at with your optical instrument, and the screen has a picket fence picture on it. Then the spacing between those picket fence, if you squeeze the picket fence together so it's real fine, you know, a lot of lines real close together, that's a high spatial frequency and fine detail. If you spread the picket fence out so there's only 1 or 2 pickets in the field of view, that's a low spatial frequency, and it's the coarser type of detail. Now in MTF, it's not as simple as a square wave, the picket fence. It's sine waves that go up and down, and you're squeezing it together or moving it apart like an accordion. And then to measure MTF, you measure the contrast between the bright and the dark of neighboring parts of that, pickets and darks. And it's at the 1 down there, the picket, the brightness and the dark next to it are indistinguishable. You can't tell them apart because there's enough scattered light to fill them in. And so that's the highest thing that you can resolve. The contrast at frequencies above that goes to 0, and it stays there.
I think part of if you look at this figure also, it says for a mirror that's not properly corrected, planetary detail suffers more than being able to resolve double stars.
Why
I
double
believe.
stars? Yeah.
What?
Why double stars?
Yeah.
Thanks, Jerry, for the picket fence
Okay.
analogy.
Let's go for 95%.
Is the modulation transfer function and the lines per millimeter reciprocals of one another?
Yeah. But it's not just lines. In order to count as the MTF analysis, it has to be a sine wave distribution of brightness in the object.
Okay.
So it's not just black and white lines and lines per millimeter, but it's the equivalent. Yes, it's inverse.
Okay, so now we have a 95% mirror. And you can see here now that the in focus and out focus are very close to each other. As far as appearance, they're getting closer. On the modulation transfer function, you notice that the blue line there is more closely aligned with the theoretical So in other words, in this case here, actually fine details seem to pop out better than some of the medium.
Are the
And
red and blue on top of each other here in the
yes,
in the MTF?
yes.
Wow.
I didn't see a red on the MTF.
Well, the thing is that they're right on top of it. I can
Oh,
see
okay.
real closely on my monitor.
Okay.
Yeah. If there was astigmatism, you would see two different lines, the red and the blue. So the point spread function, you can see here that you're approaching the central point, and that the you know, the rings are lower in amplitude. They're more aligned with the theoretical function of a perfect mirror. Now this applies also to a refractor. Refractors have issues too. So let's see here.
These do not include a central obstruction. Is that correct?
No, this is just the circular aperture.
Okay.
Okay, let me, is there a circular aperture in this? I'm looking for, no, it doesn't show here. No. Okay, cancel. So anyways, I think this was kind of instructive in a way. One more
Can
simulation.
you
Let's do
talk-
95%. No, it's 95, 98. Or, oops.
What happens if you go to 101?
Then it's overcorrected.
Yeah, okay,
okay.
105.
Well, this is just spherical aberration component. Overcorrection means the whole conical constant. Yeah. There
And
you
now
go.
you've got a bowl. Okay. That's so interesting.
And with the star test, you can tell that it's overcorrected because when you're inside focus, it's fuzzy as opposed to outside focus. So, you know.
And the size of that circle is larger on the left now.
Yeah, but you got to, you know, the thing is that being able to tell whether you've rocked it in and out exactly the same amount, you know, you have to be really careful.
I see.
And the way that I saw on the web that somebody did it was, you took two shims, you put one shim in between the eyepiece and the eyepiece holder and pushed it down exactly and went for this focused point. And then to tell the inside and outside, knowing the thickness of the shims, you take the one out, you take both of them out, you're in focus. You put both of them in, you're out of focus, and then you put one of them in there, you're back at focused. So I have a feeling because of the restriction in the focuser I had, I might not have gotten perfect inside outside. You know, I might have been deluding myself.
Well, you've got some astigmatism in here that you put in.
I did?
In the y-axis, but not
Oh
the
yeah, no, I didn't dial it in. It just, the simulation put it in there. So
Okay. What's piston up there? What does that mean?
piston is focus, I think. Okay, well, hold a second. Why don't we go on the web? Here, let me go and do, whoops. Let me just.
The first term is always piston, an aberration term associated with chief ray, which only constitutes an aberration in systems with two or more pupils differing in phase. The first term of Zernike coefficient is always piston. An aberration term associated with chief ray. Who is Chief Ray?
Chief Ray, he used to be a tribal leader, but
Polynomials, Zernike, wiki. Let's see, it does wiki Zernike. Okay, so I'm going to go and share this now. Stop share, start share. Okay, so this is what the Zernike looks like. Okay.
okay.
So this is piston. These are tilt, X and Y. This is spherical aberration. This is trifoil. In other words, where, you know, the red means it's bent up and the edges are bent down. This is trifoil. And this is a secondary spherical. And so you put
So
these.
why do you pick the piston value to be minus 16.5?
I didn't. That's
Oh.
what the simulation shows.
Okay.
Yeah.
Oh, go back down a little bit, just about one. Another one. There, stop. Null, go up just a little. No, the other way.
Okay.
Yeah, they're up.
Null. By null. Oh, I think that was a guy that was the docent on an observatory trip I took to Hawaii. Oh no, that was Null. That was the guy that went to Queensland with us as the tour guide, a docent. Huh.
Okay, well, I'm trying to find.
Landon, that was Landon. So not RJ, Landon Null.
Okay, hold a second here. Usually they have a better.
Yeah, that helps.
So basically, the Zernikes are really an approximation. I mean, there's an infinite number of terms on a
If you go
real
back,
thing.
Mike, look at that. On that image right there,
Yeah.
where piston is, the dot is right dead center. And the next one is kind of offset on the left and then the right.
That has to do with tilt. These are tilt. This is probably, these two probably are
That looks like coma.
coma. I was going to say coma. These two are trifoil. This is the second order spherical aberration.
Is that going to be stigmatism there? Right and
Oh,
left?
I think stigmatism would be on the tilt.
Oh, really?
I'm guessing.
No, this could be astigmatism, these two, I think.
You got some reading to do, I can tell.
Yeah, okay. But we're getting more knowledgeable.
Can you just for a second talk a little bit about the actual equipment, like the camera you use, that kind of stuff? I mean, I think that's
basically I used my Canon camera with an 80mm fast lens, although I think you can use a nicer zoom lens, but he recommends sort of like an 80mm, f2 or better, because of the vignetting, the possibilities with the fast mirror. And I just put it in and behind it, and I do have pictures of it, but I don't know if I have it available here to show.
Is that your Canon 6D?
Yes.
Can you use like a 50mm lens, fixed lens, and
Yeah, it might be smaller. Uh, you need to have a certain number of pixels to get,
Oh.
but I told him, George looked at the camera I had and goes, "Oh, you really got a great camera. You got lots of pixels. I got a lot less." And so I
Mhm.
think any reasonable camera, I mean, there's people doing it with webcams. Okay.
But Mike,
Um,
this is that same site that you can get the kit, right?
Yes, and
'Cause
he's
I'm
got
gonna
the
do-
videos, and one of the videos that he shows, it's sort of like you have to scroll through the other YouTubes, is what a parabola looks like, why it looks kind of wavy like that, where he simulates looking at it from an angle, a glancing angle, the
Yeah.
parallel lines.
Yeah.
And that was really good. I know that he's adding stuff to his website, and I know that
Mike,
there,
Mike, that gr5.org
yes, yes,
website /bath, it has a camera lens calculator right there.
You
Okay.
ought to send him a citation so he can look at this website and see how at sea we are.
okay, it's okay. But anyways, I think we're getting, I think little by little we are
Yes.
getting more, getting better at this. Let's see here. There's another site, telescopes or something like that, where it's really, it goes into it also.
Mike, show that website gr5.org.
Okay, hold a second. gr5 org. Okay. Let's see here.
The second one looks like.
Yeah.
Oh, what happened to it?
I don't know. Okay, home.
Oh, this is a store. This is not the org.
Oh, second, bath. I think it's,
Yeah, yeah.
okay, there we go. Let me just,
Control
Okay.
minus. Yeah.
okay, so selecting the diverging lens. So the, mine's about a 9mm or 7mm. Okay, so this is the setup right here. So he doesn't like you to use any old zoom lens. So
Any what lens?
zoom,
Oh, that's why the red X is, that's a zoom lens.
yeah,
Mhm.
because most zooms have a small focal ratio.
Yeah, they're slow.
Yeah, you get vignetting. So, let's
Oh, so it
see.
says that it works with concave mirrors, but only certain parabolic mirrors up to a certain f ratio.
Right.
So wonder what the limit is for a parabolic mirror, what the
Well,
ratio.
the thing is that the shorter the focal length, the more it spreads it out to the mirror, and so that's why. So for the longer focal lengths, you can get away with a longer focal length lens. And I'm not sure if, I think you have to be fairly accurate with your lens focal length too, just to make sure things work out okay.
I don't
Another,
think I have a lens that'll work with it.
yeah, there's quite a few. He said these are He's got this here, but if you go to his site to buy things,
Mhm.
it's the lenses aren't that expensive, you know.
Oh, I think I'm talking about the camera, the
Oh.
camera lens. It can't be a zoom. It has to be like 80 millimeters is good. When you get down to an f2, my God,
Yeah,
it's expensive.
I think well, the thing is that a fixed lens is less expensive than a zoom lens, but I was using my kit lens, my 28-105 lens, that the better of the Canon lenses,
Right.
and it seemed to get okay images. But the thing is that zoom lenses have pincushion distortion and other things
Yeah.
that you have to account for. And with a fixed lens, it's probably better. So anyways, I'm taking up too much of everybody's time, so.
Oh, we're almost
Well, you
done
got
tonight.
7 minutes.
Yeah, we're just-
I'm sorry. You know,
This is good. It's good. Believe me.
okay, so what this boils down to is you get this interferometer. You know, you get it close with a Ronchi,
Mhm.
and instead of going to Foucault, you go to this interferometer and you dial it in. And if it's 1/50th of wavelength of light accurate, you know, you could dial it in, you know. We all know that you don't need a 50th of a wavelength of light. A 20th or a 10th is probably all we could use, especially with a large mirror.
Yeah.
And speaking of a large mirror, the Oregon guys are saying that they're all starting to complain about the fact that one guy had this wonderful 28-inch Dob, but the mirror weighed 90 pounds.
Oh, is that all?
And so he says, I'm getting rid of it. I'm going to a 30-inch meniscus mirror, you know, so, you know, where it's only 30 inches. So
Yeah, then you've got to build 90 pounds worth of support structure for the glass.
yeah, well, yeah.
There's a couple of guys that take a huge mirror up to Mount Pinos. I think it's 36 inches.
Yeah.
And it's a Dobsonian, and their telescope tube is a big box. It's probably 12 feet tall or more, and it's huge. And they have a big step ladder so they can get up to the eyepiece.
Yeah, well, these guys are making he's going to make it 30-inch f2 or 2.5. No ladder.
That sounds like a soup bowl.
Yeah, it looks like a soup bowl, but these guys, the average age is like in 60 or between 60 and 70, and so they're starting to think about old age, and
old is somebody that's older than you are.
Yeah, right. Unless you look around going, oh, I'm the oldest.
I think I'm the oldest here.
Yeah. But the thing is that they're realizing, hey, I'm going to invest in this one telescope. It's going to be my forever scope. And in stock. Meniscus mirrors also are much easier to support.
They're just a ring with a hole in the middle? What is a meniscus mirror?
A meniscus mirror is
thin, a half-inch thick.
Yeah, half-inch, and it's curved. It's it's uniform thickness, so it curves.
Okay.
Oh yeah, you just melt it into a form.
Still first surface aluminized though, right?
Yeah, but some of these other guys, they're not going with aluminization. They're going with silvering. That's being a big push. When you got a 30-inch mirror and you're on retirement, it's not very affordable.
There was a big article on that, about how people were going back to silver.
Yeah, they're doing it.
That's-
They're actually getting pretty good results, and they're talking about silver in a mirror and getting anywhere between 1 year and 5 years of use out of it.
Oh, they don't spud a quartz or something on top of it?
No. They discovered that there's some sort of stuff they can spray on it that is by the same manufacturer that tends to protect it. And another thing too is they're employing a dust-free cooling mechanism where it's got a HEPA filter, so it blows dust-free air over the front of the mirror.
Wow.
Out the front of the tube, huh?
It basically forms a venturi, and it goes up towards the diagonal, and so it actually keeps the diagonal from fogging up.
Jerry, you okay?
Yeah, I had the computer problem crop up again, but I'm back.
I'm going to take off, guys. I was going to ask about the if you have any idea about the Chuck said that we really don't have a Zoom platform yet for Friday. So I don't know what we can deal with that later.
Been promised an answer by today or tomorrow, I think.
Yeah.
Right. Must be tomorrow. I didn't see one today.
Okay.
I mean, it seems to me that a Zoom account can't be that much money because I'm using the Trilogy Theater Club's subscription, you know.
We're using the museum's $150 account right now for regular Zooming, but to do webinars, it costs $650 or something. And but they did it, so somebody at the museum seemed to have done it before. So we're trying to figure out if they actually have a different account.
What's the difference between a webinar and a meeting?
Apparently about $500.
No, but a meeting should be a meeting.
So everybody gets involved in a sense, right?
Right,
Well,
but the thing is that the host of the meeting has the ability to mute and unmute people.
Yes, but people can unmute themselves, but the
No,
webinars are, the host can do that a little easier. I think it only allows certain people to come in unmuted, I think. Not totally clear.
No, because my synagogue uses a Zoom, and it's sort of like the host has the ability to mute and unmute people at will.
Yeah, I mean, I can do that. I can click on mute people if someone's making too much noise, but you can unmute yourself. I think in the webinar you have more control.
No, you can't unmute yourself.
So if you
I
get
like it.
blasphemous, he can just turn you off, huh?
Yeah.
Well, see, if I mute you right now,
Yeah.
muting Mike. So Mike, can you unmute yourself?
Yeah, I can.
Yeah. Mhm. So
Guy?
maybe the synagogue is using a webinar form.
Yeah, and it's just paying for it.
Yeah. Okay. Well,
Okay.
hey, good night for everybody. So that was
Okay.
kind of interesting, all that, Mike.
It was
Yeah, Mike,
okay.
really
I'm glad
appreciate
I mean, I'm sorry if I hogged it up and people couldn't
No, it
talk.
was
You
great.
did.
You
did.
really liked it. Okay, good.
You
Yeah.
dropped
we need-
all
I
wanted-
guns out.
We need
I want
Jerry
to talk
fi-
about
do his.
contrast improvement in telescopes, but I'll wait for a week.
Okay.
Okay, Bruce, good.
I've been doing a lot of study on that.
Okay,
Mhm.
good.
That sounds good.
Good evening,
All right.
guys.
Okay,
You
we'll see you.
guys,
Take care.
ending
Okay.
the meeting. Bye-bye.
Bye.
Bye.